Thank you. Hello everyone, my name is Hassan Saghi and nice to meet you again. My presentation is about our recent publication on the pitch control of floating offshore wind turbine. As you know, floating offshore wind turbine or floating offshore wind energy is the primary solution for expanding wind power generation into deep water in the future. However, the stabilization of floating offshore wind turbine is a main issue, and we have some methods or devices to control and mitigate the motion of floating offshore wind turbine, including mooring line, additional control actuations, something like TLB, TLC, and TLB, and so on, and delay pitch control. So the main objective of the research or all research was the utilization of different devices, including a new liquid damper called bidirectional tuned liquid damper or BTLD, and also a skirt into the body of a large type floating offshore wind turbine substructure to control the pitch movement of the floating offshore wind turbine. But BTLD or bidirectional tuned liquid damper, in these figures you can see on the top left and right a schematic sketch of a BTLD and BTLCD. The red color is water and blue one is air. On the down left and the right, you can see the integrated model, integration of a large type of offshore wind turbine and a BTLD on the left and a BTLCD on the right. We try to find the optimum geometry for BTLD and BTLCD to mitigate and control the pitch motion of the floating offshore wind turbine by using a device, a baffle in BTLD and orifice in BTLCD. Because if you don't have a baffle at the middle of the BTLD, we cannot control the pitch motion because it's very important. We can find the optimum baffle at the middle of the BTLD. In this figure, I think you can see here we have a baffle. Actually, baffle makes a lag between the flow inside the BTLD and outside, so we can control the pitch motion. And also for BTLCD, in this figure you can see an orifice. By finding the optimum orifice, we can mitigate the pitch motion. So baffle and orifice are very important in this research. So about the literature review, this is a new topic, and we can find only some paper recently published in the journal. For example, this paper from Park and his colleagues, I think it's published in 2023, I think it's 2020. Sorry. In this paper, they used the liquid damper, column damper, in a nozzle of the TLP, and you can see this figure. And the result demonstrates the effectiveness of the TLCD in reducing extreme load. And in another research or paper from Yu et al. And his colleagues in 2023, in this paper they're starting inside a tuned liquid multi-column damper. There was a multi-column model for mitigating rotational motion for a semi-submersible in this kind of floating turbine. And they show that TLCD can be better alternative to paper. They investigated the vibration and suppression of the barge type by using a TLC. However, this paper is there is a difference between this paper and the other paper, because in this paper they modeled a simple barge without moon pool, but in our research we consider or model a barge type with a moon pool at the middle of the barge, the substructure or barge. Okay, so in our research we also modeled a new type of barge, octagonal actually. We modeled different cases, different geometries, so that the volume of the barge was constant. And to find the optimal geometry or optimal integrated model, at the first step we modeled a huge number of cases of the BTLD, that you can see in this figure. And we selected only 10 cases. In this table you can see, 9 cases. We selected 9 cases, the optimal one, and we integrated these cases with the barge. However, I have to explain here, we have 9 cases for different dimensions for the barge, for the BTLD. But here we have a baffle with different heights. So if we have 9 BTLD geometry with, for example, 4 baffle height, actually we have 36 cases, because for each case we have 4 baffle heights. So totally we have 9 multiple 4 is 36 cases. We integrated the barge and BTLD and model, and in this figure you can see pitch motion of the integrated model for different cases. And here are only some cases, case 1, 5, 7, and 9. The x-axis is the time, and the vertical y-axis is the pitch motion of the floating offshore integrated model. Okay, in these figures you can see we compare different cases. Here you can see case 1 to case 9, and the x-axis is the baffle height, 0, 1, 2, 3, 4, 5 meter. And here is the maximum pitch, and here is the maximum heave. By comparing the different cases and different baffle heights, we selected the optimum geometry and optimum baffle height. I think case 9, and with 4 meter high for the baffle is the optimum case. We selected as the optimum case. And we did also a sensitive analysis of the filling water level inside the BTLD, because as I explained, we have some water inside the BTLD. We can define a different water level. So we did a sensitive analysis for the filling water level, and we compared the results, and based on the pitch motion we selected and found the optimum water level. And also there's another parameter is very important about the BTLD, is the location of the BTLD inside the barge. So we did another sensitive analysis of the BTLD location related to the bottom of the barge. And in this figure you can see this parameter V is the distance between the bottom of the barge and bottom of the BTLD from 0.5 meter to 4.5, and the optimum location is 2.5. So First, we define different geometry for BTLD, and we found the optimum dimension or geometry, and also optimum buffer height, and then optimum water level, and optimum location. After finding the optimum case, here we modeled the suggested geometry for different wave periods. In this figure, we can see the model different wave periods from 8 to 20. And in this figure, and we compare maximum pitch motion of the barge. In this figure, the blue one is the actually floating offshore wind turbine without BTLD, and the red one, this one, the red one is the integrated model, integration of floating offshore wind turbine and BTLD, and you can see for the wave periods less than 17, the pitch motion is less. Around the natural period, it's around, I think, 30% less relative to the original floating offshore wind turbine. However, for the wave motion, you can see the suggested model, the integrated model, has a bit more heave motion related to the original floating offshore wind turbine. After modeling the BTLD, we follow a similar procedure. And in this figure, you can see a schematic sketch of the BTLC with different parameters. And we actually model different cases and compare different cases together. Here, the x-axis is the case number, and also we model for different OP. OP is the opening percentage of the orifice, and we found the optimal case based on the maximum pitch and heave similarly. And also we did a sensitive analysis of the opening percentage, and based on the pitch motion, we found the optimal opening percentage around 60%. Till now, we modeled only a constant geometry. We consider only one geometry for the floating offshore wind turbine, substructure or barge. But here we model different cases for an octagonal floating offshore wind turbine. You can see in this figure. We model or define different dimensions so that the total area was constant, or the volume of the bar was constant. And then we model, we model different cases. In this figure, you can see we have three cases. The first one is the octagonal floating offshore wind turbine without BTLD. The second one is integrated octagonal and BTLD, and also octagonal and BTLCD. And the y-axis is pitch and heave. We compare different cases. And in this figure, A is this parameter A. Here. We compare different cases and from the optimum geometry for the octagonal. Finally, we compare all cases we modeled. The first one is the barge, simple barge. The second one is integrated barge and BTLD, barge BTLC, octagonal BTLD, and octagonal BTLCD. You can see, for example, this figure is about E, but in this figure, we can select the optimum geometry or optimal model for different wave periods. For example, for this wave period, this one is the integrated orthogonal and medial is the optimum system or model. Or for other wave periods, you can select the optimal case or system. Okay, this is our first published paper in ocean engineering, titled Pitch Motion Reduction of a barge type floating offshore wind turbine, substructure using a bidirectional liquid dampers. And this is the second paper, bidirectional liquid damper for stabilizing floating offshore wind turbines substructures. Okay, but the second subject we wrote was about a skirt. In this figure, you can see a new geometry we suggested. It includes a trapezoidal barge and a skirt. To find this geometry, we follow a sequential procedure to find the geometry or geometry. The first step, we model a square bar, simple bar with an orthogonal neutral, so that the total area of the neutron was constant. So we can find different cases and we compare different cases based on the RAO of and pitch. And in this figure you can see the x-axis is the A is the parameter you can see in this figure, and we compare different cases. From the optimal geometry for the element. This figure is deep and this one is pitch or different wave. And in this research, actually we model for different wave angles from 0 to 45. Next step, we modeled an orthogonal platform with the optimum motor we selected in the previous section, and we compare different, we model different platform geometry and compare this figure. You can see our different C in this figure you can see is a answer, and we selected optimum. In the next step, we added a skirt with the length of L. S is the length of the skirt, and located HS above the bottom of the barge. So we model different cases and we compare together. In this figure, you can see the area of pitch for different length and also for different location. There are a huge number of graphs in my paper, but here I will do something because of time. And finally, we modeled a trapezoidal